Hello everyone, and welcome to this introduction to the concept of thermal radiation. Now, the idea of thermal radiation is that if we put two objects in a vacuum, so there's no material between them to allow for conduction or convection, we can still observe heat transfer between the objects. And this is due to what we call thermal radiation. Thermal radiation is emitted by all matter, and it's due to oscillations in electrons from the thermal energy of the material. So we have thermal radiation occurring in wavelengths in the infrared and visible light and a little bit of the ultraviolet spectrum. And then here at much shorter wavelengths or higher frequencies we have gamma rays, X-rays, and ultraviolet. And these are of interest for radiation protection in nuclear engineering. And then at longer wavelengths we have things like microwaves and radio waves, which have different uses. Now these waves travel at the speed of light, just like all electromagnetic radiation. And we also need to make a note that if two objects are at the same temperature, the net radiation exchange between the two objects is zero. The same amount leaves as enters an object because they're in thermal equilibrium, so we have no heat transfer, no net heat transfer. So for our purposes, we're going to consider radiation to be a surface phenomenon. It only happens at surfaces. Now, this is true for opaque materials. There's a lot of opaque materials out there. However, for certain materials like glass or gases, anything that's transparent or semi-transparent, radiation is what we call a volumetric phenomenon. It can be absorbed or emitted inside the object. We're not going to consider those during this unit. So there are several types of important heat flux that we need to consider here. The first one is the emissive power. The emissive power represents the amount of radiation that's released from an object due to its temperature, and it follows the Stefan-Boltzmann law. So E equals emissivity of the surface times the Stefan-Boltzmann constant times temperature to the fourth. We also have to consider the irradiation. The irradiation is the amount of radiation that's coming to the surface, and then it can be either reflected or absorbed. So we can divide the irradiation into the reflected part, characterized by the reflectivity, and the absorbed part, characterized by the absorptivity. And once we have this information, we can look at what we call the radiosity. The radiosity represents the net radiation leaving an object by both emission or reflection. So we take the reflection and we take the emission and we add them together to get radiosity. Now this isn't very important for some of the simpler two-body problems that we're going to start with, but later on it becomes very important for multi-surface problems, more complex problems. And once we have all of these definitions, we can also look at the net radiation heat flux. So the net radiation heat flux is going to be the emitted radiation minus what's absorbed by the surface. So you know we don't see the reflected radiation here. It doesn't interact with the material, it just bounces off. So we have the emission and the absorption that make up the net radiation heat flux for the object. We also need to discuss what we call intensity. Now the reality is that thermal radiation has a spectrum over a wide range of wavelengths. So just like gamma radiation and so on, there's a spectrum. The peak location, the shape, and the magnitude of the spectrum depend on both the surface type and the temperature of the surface. And it's also possible for surfaces to emit in what we call preferential directions. So we start by defining the spectral intensity. Now the spectral intensity here you can see depends on the wavelength and the direction. And so what we're basically doing is taking the entire spectrum and we're breaking it down to look at this particular wavelength, and here's all the radiation emitted at that particular wavelength, and then we move over here to the directional distribution, and at that wavelength how much of the radiation is emitted along this line, and that gives us the intensity. So it gives us the rate at which radiation is being emitted at a particular wavelength in a particular direction. So then we can integrate this to compute what we call the heat rate for the surface. So we integrate this over what we call the solid angle, and that is going to give us the solid angle for a hemisphere, for instance. So we can see here that a solid hemisphere has an angle of 2 pi steradians. Steradians is how we measure solid angles. That means for a sphere we have 4 pi steradians. Now, this type of integral necessitates that we work in spherical coordinates for simplicity, but it's very similar to accounting for directionality in neutronics, where we use the solid angle omega to characterize the direction that the neutrons are coming from. It's also worth noting here that radiation can be emitted into any part of a hemisphere above a flat surface. So if you have a flat surface that's hot and it's emitting radiation, it can be emitted in any of these directions over that hemisphere above it.